Hi, so this time we're going to explore what happens when you have a system of linear differential equations with complex roots. So let's start off with a system of linear differential equations. Let's say x prime is x1 minus x2, and x2 prime is x1 plus x2. All right, if we set things up this way, what you end up with is a uh, linear system expressible as m times the vector x is x prime, where m is the matrix 1, negative 1, 1, 1. And just looking at this matrix, we could tell that it's going to have complex eigenvalues. 1 minus lambda times 1 minus lambda is 1 minus lambda squared, which is a parabola. And since its root has multiplicity 2, it sits on the x-axis. And then when I subtract negative 1 from that, I pop it up a bit, and so it has no real roots, so its roots must be complex. So um, M definitely has complex eigenvalues. Now to find the eigenvectors for that, we're going to skip over the difficult part, and it's extra annoying because of the complex values. So, but if we pop it in Sage with 1 minus 1 as the first row and 1, 1 as the second row, we get this system, uh, or we get these eigenvalues and eigenvectors. 1 minus I is the first eigenvalue, so let me write that down. Lambda 1 is 1 minus I, and that's associated with eigenvector 1i, and then lambda 2 is 1 plus I, and that's associated with eigenvector 1 minus I. And so let me put a little comment there too. And so I want us to think back to when we did second order differential equations and higher order differential equations when we had complex roots, right? Uh, what we did was when we had the complex roots, those are expressible as some e to the I theta and constant multiples of things of that nature, which we wanted to rewrite into real valued solutions. And the way we did that was by expanding the e to the I theta into sines and cosines, cosine something, I sine something, and they would come in conjugate pairs, and then we would use the fact that we could take linear combinations of them to cancel out the complex parts one way or the other to get two real valued solutions who are linearly independent, right? And so if we look at our roots here, we have the minus I, positive I minus I. So it seems as if these solutions also come in conjugate pairs. And since they also come in conjugate pairs, we can leverage the same sort of techniques to get complex parts to cancel out and be left just with real stuff. And so let's just go ahead and work out what our two solutions might look like here associated with these roots. So we were playing the same game that we played in the last video. One of our solutions would be something of the form 1 minus, sorry, 1 minus I times, I'm sorry, it'll be 1I e to the 1 minus I. All right. And this thing, sorry, quantity t. And so what we want to do is rewrite this as we can pull the e to the t out. The 1i I'm going to express as 1, 0 plus I 0, 1, and then the e to the minus it, that's expressible as cosine of t minus I sine of t, right? And so we do this because what we want to do is totally expand and recombine this thing to just be real and complex parts. So when I multiply all of this stuff out and recombine, I get e to the it 1, 0 cosine t. And then I'm go ahead and say I 0, 1 times minus I sine of t gives me positive 0, 1 sine of t. And then I get I 0, 1 cosine of t. And then this I, or this 1, 0 times that gives me minus I 1, 0 sine of t. All right. So that's not the prettiest thing in the road, but it's done. And that is the solution that corresponds to this eigenpair, this eigenvalue, and this eigenvector. If we play out the same game with this pair, our next solution is going to coincide with 1 minus I e to the 1 plus I t, and that's going to correspond to e to the t, still 1, 0, with the cosine, and then I have minus I 0, 1, minus I 0, 1 against positive I sine gives me positive sine with my 0, 1. I'm just skipping over the intermediary step, basically. And then, see, 1, 0 against the positive I sine gives me plus, let me go over here and say plus I 1, 0 sine of t. And in between those, I have the minus I stuck to the positive cosine, so minus I 0, 1 cosine of t. All right. And so I want us to look at these two things again. And again, it seems like they come in conjugate pairs. I get a real part that's identical to both, and I get an imaginary part whose signs are the opposite of each other. And so the same game we played previously, whenever we did this, we can pick our coefficients to cancel the real parts, we can pick our coefficients to cancel the imaginary parts, and that will give us a pair of distinct linearly independent solutions. So let's see what that would look like. So remember that I can take C1 times this whole thing maybe that's not the right place to write it. C1 times this whole thing plus C2 times this whole thing, and any possible choice for C1 and C2, including complex choices, is valid. So if I go back to that and I let C1 and C2 both be a half, and I look back at what might happen there, I get that half of this plus half of that means these two cancel, and this real part is preserved. So I get then as a solution, 1, 0 cosine of t e to the t plus 0, 1 sine of t e to the t. So that is a solution. I'm going to call this solution W1. And then my next solution is going to come from canceling the real parts and turning the imaginary parts real. So if I hit this guy with a minus I, this becomes positive 1, this becomes negative 1, this becomes negative 1, this becomes positive 1, and I would get this whole thing turned real but doubled. And so if I let C1 be minus I over 2, and I let C2 be I over 2. Now let me just think if this is the actual choice that I want. No, I don't think so. I think I want to switch my sides. This is purely an aesthetic choice, by the way. And the reason I chose this is so that when I hit this guy with minus I over 2, this is the positive term, right? And that's the negative term. So what I will end up as my solution is 1, 0 sine of t e to the t minus 0, 1 cosine of t e to the t. I'm going to call that W2. And we will note then that any linear combination of this W1 and this W2 is also a system, or is also a solution to this system. And not only will they be a solution, I believe that W1 and W2 are linearly independent, because I can't multiply cosine by anything that will give me sine, no constant value anyway. Sine and cosine are linearly independent, and that means these two solutions must be as well. So in general, my x value is C1 W1 plus C2 W2. These are new C1s and C2s. Of course, they're not the same as these, right? But we're just reusing that out of a sense of familiarity. And that means that x1 is, C1 cosine of t e to the t plus C2 sine of t e to the t, right? I'm combining this with that, and then x2 is going to be the second entry, which is sine minus cosine C1 sine of t e to the t minus C2 cosine of t e to the t. And now if we go ahead and look at that, that is our general system of equations. Now we're going to go ahead and verify this, but we're not going to verify this formally using the algebra. We're just going to kind of visually verify it. And in a lot of ways, that is the more practical thing to do. So I'm going to skip over using t's and x1s and x2s just because Desmos doesn't like it as much. I'm going to say that f of x is c1 cosine of x e to the x plus c sub 2 sine of x e to the x. And let's throw in some sliders there. And so if these are both 1, then this is what my solution looks like. It's a fairly gnarly thing to behold, to be honest. And then the thing to note is that G is similar, except we have sine minus cosine, right? So we get something like that. All right, great. I'm going to undraw both of those because I want to think back on our original system here. We have that x1 prime is x1 minus x2, and x2 prime is x1 plus x2. So I'm going to go ahead and draw f prime of x. I'm going to compare that to f of x minus g of x. Going to go ahead and make that dashed. And look at that. It falls right on top of my f prime of x line. And if I change either my parameters, yeah, it looks like it follows perfectly. So it really does seem like f prime is f minus g. F and g are these things. And again, this shouldn't be too surprising since we did work out all of the math to do this. Now note this doesn't constitute a proof, right? But it's pretty convincing. I'm pretty convinced. And then given the fact that we did all of the algebra here, right, these two things together tell a fairly compelling story to me. The next thing to check then would be g prime of x, so let's uncolor those, and let's compare that to f of x plus g of x. And again, that looks like it falls right on top. Gonna go ahead and dash that. Yeah, and there we go. Once again, it looks as if f and g are totally in line with each other, right? Sorry, not f and g, but g prime and f plus g. All right, so I'm convinced then that this is in fact my general solution. And as is the case with these, we'll throw in an example to discuss what happens if there are if we're looking for some particular solution. So let's say I want f of 0 to be, let's say 1, and g of 0 to be negative 1. Actually, that's not exactly right. I'm getting confused. It's x1 and x2, right? I'm just calling them f and g for the purposes of Desmos. Well, if I go back to my previous slide and look at those situations, if I plug in 0 in for x1, right, the sign goes to 0, e to the 0 is 1, cosine of 0 is 1. So what I'm really saying is that c1 is 1, right? And similarly, if I go back here and I say, well, x2 of 0 has to be 1, well, sine of 0 is 0, cosine of t is 1, e to the t is 1. Sorry, if cosine or x2 of 0 is negative 1, there's already a negative there, c2 must also be 1. right? You can check with C1 being 1 and C2 also being 1, give us that at time 0, x1's 1 and x2 is negative 1? It does seem so. And again, and this time, if we believe our general solution, we can actually verify this here. If I let C1 and C2 both be 1, I'm going to uncheck those. I can ask myself, what is f of 0? It's 1. What's g of 0? It's negative 1. So there we go. It satisfies our general system. Or sorry, our initial conditions. It is the particular solution that satisfies initial conditions. It's 9:30 at night. It's been a long day. And we can go ahead and plot those to see what that might look like. Although, honestly, this isn't giving me too much insight. It's just a bunch of vertical lines at some point, and it just becomes not really helpful to see that. But the particular computations here are. All right. Well, thank you for paying attention. See you in the next video.